Welcome back to Fundamental Concepts in Chemical Engineering. Today we're going to move out of our science and math review and into sort of the first set of concepts in chemical engineering, which is mass and energy balances. By the end of today, you should be familiar and comfortable with unit conversions, the concept of interpolating data, the fundamental equation of chemical engineering, single unit mass balances, degree of freedom analysis, and multiple unit operation balances. So now let's talk about units. So hopefully these are all familiar with you, but there are many different units that express the same concept. So, we could express mass in terms of kilograms or grams or pounds mass. We can think about length in terms of meters, centimeters, feet, inches, etc. In chemical engineering, we're often required to sort of switch between units because some things are expressed in English units, and some things are expressed in metric. So let's go through how we can do some simple conversions. Let's start out with, this simple question: how many seconds are in 2.5 hours? Well, we can go to a lookup table. I mean, in this case, we should know this, that 1 hour is 60 minutes and 1 minute is 60 seconds. We then construct a unit conversion table, which is a horizontal line with a bunch of vertical lines. On the left, we say what we know, what we're trying to convert from. And then we're going to have a series of conversions, which will allow us to convert or switch units off of hours into seconds. So we have our knowns, right? There's just a single unit. It's 2.3 hours, so that goes on top. And then we are going to write down in each of these sort of square pockets the conversion. So this is 60 minutes per hour, and we write it in this way so that the hours are going to cancel out. Right, so any unit that we have up here that we want to get rid of, I need to have it down here. Right, okay, so then I can do the same thing. I have 60 seconds per minute. I'm putting it in this order because I want to cancel these minutes out. Right, and so the hours are going to cancel out, the minute cancels out. So then all I need to do is multiply each of these, multiply everything across the top, and then divide by everything along the bottom. In this case, it's pretty straightforward because on the bottom they're just ones. So I take 2.3 times 60 times 60, and that gives me 8,280 seconds. We can have something a little bit more complicated in converting a density of, say, water, which is 1 gallon per milliliter, into kilograms per cubic meter. From either our own knowledge or look up tables, we can say that there's 1,000 grams in 1 kilogram, 1 milliliter is 1 centimeter cubed, and there's 100 centimeters in a meter. So once again, I construct my conversion table here on the left-hand side, where I'm going to put my knowns. I have 1 gram per milliliter because we have this divisor of the milliliters that's going to go under the line. I then can start, using my knowns to fill in this table. I have grams here, so I need to get rid of grams. So I can put the 1,000 grams here, so that leaves me with 1 kilogram up here. This is going to make sense now because when I eliminate the grams, I'm left with kilograms on top. That's what I'm looking for. I now need to get rid of the milliliters, so I need to use this first conversion piece of information. I'm going to have milliliters up on top, centimeters cubed on the bottom. Right, so 1 milliliter per centimeter cubed. Great. My milliliters cancel out. I'm now left with kilograms per cubic meter. Sorry, per cubic centimeter. We're getting closer. I now need to get rid of the centimeters. I put 100 up on top because that's going to get 100 centimeters per meter with the centimeters on top, because that will get rid of one of these 3 centimeters. in the centimeter cubed. And I need to do this a total of 3 times to get rid of the 3 centimeters. And then that gives me 1,000 kilograms per cubic meter. All right, so we can do this with almost any temperature unit. The only one that's a little bit funky is temperature, and that's because the temperatures not only have different scales, but they have different zeros. So when I want to convert between, Kelvin and Celsius, I need to use this equation. I need to use these equations. One sort of last note on units. So pressure, which is often measured in atmospheres or pascals, bar, millimeter mercury, etc., are also measured in 2 different ways. So the first being absolute pressure, which is the true pressure of the gas. Think PV equals nRT, that's the P. But there's also a gauge pressure. And so this is the difference in the absolute pressure and the surrounding atmosphere. This is useful because if you're wanting to pressurize some sort of gas to move it around, you may want to know what the pressure is relative to the atmosphere it's working in. Sort of conversely, this is often used because gauge pressure is easier to measure. Okay, so often in chemical engineering, information is stored on charts or in tables. So in a chart, we might have some sort of height versus some sort of day. I mean, this is just an example chart, and we'd have, let's say 3 points here shown in red. But I'm interested in finding information about what happens at day 3. Well, if I have a chart, I can go to my line and I can then read off the information on that chart. If I don't want to construct, or if the data is tabular rather than displayed or contained in a graph, I can do what's called a linear interpolation, where I take 2 points of known data, so say this red point and this red point, and then I can fit a line to that using sort of y equals mx plus b. Right, I can fit m and b via, say, this equation, and then I can use that resulting line to get the data anywhere in between those 2 points, right? So this is the resulting equation, y equals y1 plus x minus x1 over x2 minus x1 times y2 minus y1. I can use this same sort of equation if I know, in this example, how high I want something to be. I could then rearrange the equation to find out how many days it would take. A lot of times in chemical engineering, though, things have exponential behavior. So it's really difficult to show information on plots that are purely linear. So, for example, we see a lot of things where some arbitrary value y will change with our dependent variable y will change as an exponential of our independent variable. And this is very difficult to draw. So what we do is we will display this information on a semi-log plot. So down at the bottom, our independent variable is our sort of linear system, our linear scale, but our dependent variable, so this y set, is drawn on a log plot. So you'll notice, so this is called a semi-log plot because we have log on one side and linear on the other. And what you'll notice is these lines are no longer evenly spaced in a linear sense, right? So the space between 1 and 2 is large, and then it goes, a little bit smaller to 3, 4, 5, 6, all the way up to 10. And then we have another big jump as I move up the next set of logs. So I can read this information off just like before, right? If I'm at 0, I go up, I go over, it's 1. Perfectly fine. If I want to go to, say, 1, I go up, I go over. I need to be aware that I'm not sitting at, 2 or 3. I'm sitting somewhere in between um, uh, 2 and 3. But I need to use sort of this non-linear approach, right? So, the first big step would be 1, and then sort of things get a little bit finer in there, right? I can take this, excuse me, to the next extreme where I have a log-log plot where not only y is on this sort of log scale, but x is also on the log scale. So um, as you go forward in chemical engineering, these are the types of, or these are the ways that information will be presented. All right, now that we have our feet set in and feeling comfortable with plots of data and um, unit conversions, let's move on to the fundamental chemical engineering principles. Almost all of chemical engineering can be described by this single equation. Accumulation equals input minus output plus generation minus consumption. Where does this come from? This comes from the fact that mass and energy can neither be created nor destroyed, only transformed. Right? So mass accumulation in some sort of vessel or system must be equal to how much of mass is put in minus how much comes out plus um, generation in terms of just pure mass. This isn't generated or consumed, right? But if I think in terms of, a chemical reaction, I can have changes which is where generation and consumption would come from. Okay. And then I can also just write it a little bit more in shorthand. A equals I minus O plus G minus C. Okay, so let's make some simplifications and generalizations on this equation. Sorry, let me go back before we do that. For sort of the rest of your time as a chemical engineer, everything is going to be thought about in terms of this equation. And the trick in chemical engineering is, how do I assess what these terms are? How do I account for the accumulation, the input, the output, the generation, the consumption? And what these terms are can be quite complicated. Often can be in terms of differential equations um, and complex structures. But it all boils down to this general equation. Okay, but for today, we're going to sort of leave off the high-end calculus and math, and we're going to just think about these in terms of mass balances. So let's look at some simplifications and generalizations about these terms. So the first one that we'll see a lot in chemical engineering is a continuous process or a steady state process, right? So this means that, nothing is accumulating. That whatever's happening in that system is not changing with time, therefore the accumulation is 0. Also see, and this is what we'll deal with today. We'll also see a lot of times something called a non-reactive process, or have non-reactive species. When I have non-reactive species, or nothing is reacting, then my generation and consumption are 0. I can have a few other types of processes that we may see in terms of chemical engineering. So just to get some vocabulary set, so a continuous process we've already discussed, so the accumulation is 0. We also can have what's called a batch process, where I put all of my um, material into a vessel, and then I do some sort of reaction or separation or whatever I want to do, but nothing's moving in or out of that vessel in time until the end of the process. And then I remove everything. So when I'm thinking about that process, um, while it's operating, you know, uh, the input and the output are zero, but the accumulation, the generation, and the consumption may or may not be zero depending on what's happening. We can also have what's called a semi-batch process, um, where usually we think of a semi-batch process as a combination of the continuous and the batch, where I have some amount of stuff in a reactor to start, and then I'm continually adding um, some material over time. In that case, the output, right, nothing's coming out of that reactor. Um, so uh, the output is zero. I can conversely have a different semi-batch process where everything starts in the reactor, nothing new is added, and things only leave, in which case the input would be zero, right? So either input or output are zero. Like I said before, we can have non-reactive systems where the generation and the consumption are zero. I can have a transient system, so this would be, some sort of type of semi-batch, where we have I or O or accumulation or any of these pieces are a function of time. And then once again, steady state, where we have nothing being a function of time. Okay, so let's take this and put this into practice using what we're going to call mass balances. In essence, what mass balance problems are said given some sort of inputs or outputs to a process, figure out the unknowns. What are how is material moving through a system? So I think that this is best sort of seen and understand through an example. So let's say we have two streams of liquid which are continuously entering a mixer at 1 kilogram per second, and a second stream that's going to enter that mixer at 3 kilograms per second. And so we want to know this continuous steady state, how much is coming out. So I'm going to draw this diagram. You should always start your problem solving by taking the word problem and converting it into some sort of diagram. So I first draw my mixer, right? I'm entering a mixer. I have two liquid streams. So I have two sort of lines, arrows showing that something's going in, right? The arrow is pointing into the mixer. I have one stream that's leaving. So I have one arrow that's coming out of the stream, of this mixer. I'm also going to label my streams. I have stream one. That's going to be this first stream. I have a second stream, stream two, and then I have a stream three, which is leaving the system. I always want to label these so I can keep track of what's happening where. So 1, 2, and 3. You'll notice that I have these labeled with an M with a dot on the top. That means this is the mass flow rate. So the dot on top is going to say that this is, a rate. It's not just a one-time infusion of material. Okay, so this diagram can be called a flow chart or a flow diagram or a process diagram. And this is going to be what you're going to see, in the rest of your time as a student and as an operating chemical engineer. We really like to think of things in terms of flow diagrams or process diagrams. Because we can then very visually simply see what's happening, how material is moving through a system, right? So I have two streams that are going in. I have one stream that's coming out. Okay, so now let's go back and think about how we can determine how much comes out. So we're going to go back to our equation. We have accumulation equals input minus output plus generation minus consumption. And because we aren't told that anything is reacting, we can assume that there's no generation or consumption. And because we're having a continuous steady state process, there's no accumulation. So we're left with this equation that 0 equals input, so what's going in, M1 and M2. So they have plus signs. What's coming out is M3. Very good. So now we've converted this word problem into a diagram. Then we've used our fundamental equation of chemical engineering. We've looked and seen which ones are 0. We've identified what our inputs and outputs into this sort of mass balance is. And we've now derived an equation that will tell us how we can relate M1, M2, and M3. Now, because we know what M1 and M2 are, and I don't know what M3 is, I'm going to move that over to the left-hand side. And then I can, plug in my numbers, right? M1, we were told was 1 kilogram a second. M2 was 3 kilograms a second. Therefore, the amount leaving my mixer is 4 kilograms per second. My problem is solved. Okay, so this is our first mass balance. This is shown as a very simple example, but as we'll see in a second, things get complicated fast. Okay, let's look at this from a slightly different perspective, but still keeping that relatively simple flow diagram. So we still have two streams of liquid continuously entering a mixer. We have one stream where we have 1 kilogram per second entering, and now we have 3 kilograms per second leaving the mixer. And we're tasked with finding out how much liquid 2 is entering the system. So again, I have that same process flow diagram that I would draw. I have my mixer, mass flow 1, mass flow 2, mass flow 3. I have my equation, accumulation equals input minus output plus generation minus consumption, right? There's no accumulation, there's no generation, there's no consumption. I have M1 plus M2 equals M3. Well, what do I know? I know M3 and I know M1, so I want to isolate M2. Right, so M2, that flow rate is M3 minus M1. Okay, I can then go plug in my knowns, 3 leaves, 1 enters. That must mean that the second mass flow rate is 2 kilograms per second. Right, so this is to illustrate that, in chemical engineering, oftentimes we don't necessarily know we don't always know what's entering and leaving. Sometimes we know what we want to leave, and therefore we're trying to go back and figure out, okay, how much do I need to put into a system? Okay. All right. So looking through these processes, we can look and see, do what's called degree of freedom analysis. And this is going to tell us if we have enough information to solve a problem. Okay, so this is a handy tool to sort of help us figure this out. So once we have our flowchart drawn and we can carry out this degree of freedom analysis. In the degrees of freedom, I look at how many unknowns I have, right? So I can count up all of my variables that I don't know what they are. I can look at how many balances I can write. So that's, a mass balance. I can look at and count up any other equations that I have. And this might relate, say, fractions, right? I may know, what percentage of something exists. And these are going to give me the number of degrees of freedom in my system. Okay, so if I have 0, I can solve my system. if I don't have enough, I have more unknowns than equations, my system is overspecified, and the opposite is true if I'm then sorry, underspecified, and then I'm overspecified. All right, let's look at a more complex mass balance and see where all this stuff can be used. All right, so let's consider a liquid mixture containing 45 weight percent benzene and 55% toluene is fed into a distillation column operating at steady state. I'm going to make a quick side stream. A distillation column is there to split streams and take a mixture and separate it into two outflowing streams. Product streams emerge from the top and the bottom of the column. The top product stream contains 95% weight percent benzene, and the bottom contains 8% of the benzene fed to the column. The volumetric flow rate of the feed stream is 2,000 liters per hour, and the specific gravity of the feed mixture is 0.872. Determine the mass flow rate of the overhead product stream and the mass flow rate and composition of the bottom product stream. All right, so this is a very classical chemical engineering problem. I know bits of information about the system. I know how much is fed. I know what my desired concentration is in the top stream. And I just need to solve for all of the other flow rates. So just like I said before, the first thing is to draw a picture of what's happening. Right? Always draw a picture. So I have my mass 1, which is entering my distillation column. I have this top product stream, right? So I'm going to call this mass flow rate 2. I have some that's leaving out of the bottom that we'll call our mass flow rate 3. I know additional information about the system, so I'm going to label this in my picture so that all the information is in my diagram. Right? I was told in looking at the inlet stream that my liquid is 45 weight percent benzene and 55% toluene. Right? So I can write that down here. Right? 0.45 kilograms of benzene for every kilogram of this stream, and 0.55 kilograms toluene per kilogram of the stream entering. I know additional information about the stream in that I have 2,000 liters per hour entering, and that my specific gravity is 0.872. Very good. So this is all of the information that I've been able to extract from the problem statement in this handy-dandy labeled diagram. Over on the right-hand side, I can add additional information about what's happening leaving the distillation column. I was told that the top stream products contain 95% benzene by weight, and so I can rewrite that out. So 0.95 kilograms of benzene per kilogram leaving here. And so if it's 95% benzene, that must mean that the other 5% is toluene, right? So I have 0.05 kilograms of toluene per kilogram of that stream, right? If I know information about, one of these, I sort of know what's happening with the other because, the percents must equal, or the fractions must equal 1. All right, so at the bottom, I know sort of less information here. I only know that 8% of the benzene, which came in, is leaving out here, but I don't know any specific numbers. Okay, so now that we've constructed our mass balance, now that we've constructed our diagram, We can start in on doing the mass balance. To do this, I need to know how much, I need to know one of these masses. And I don't directly know that, but I do know the volumetric flow rate, right? So how much volume is coming in per hour. Therefore, I need to convert this 2000 liters per hour into mass, right? I need to convert it into something that's conserved. Mass is conserved. Volume is not conserved. I can now convert this 2000 liters per hour into a mass using my conversion table. So I first write down my 2000 liters of liquid, right? So that's what's coming in per hour. I now need to have a way to convert liters into mass. I can do that via the density, but we don't have a density, we have a specific gravity. So we need to remember that specific gravity is the ratio of the density of any liquid to a reference case. And when we're not specified, that reference is taken to be water. Okay. Um, so in this case, we have 0.872 equals the density of this inlet liquid over the density of water. Water has a density of 1 kilogram per liter. Therefore, the density of the liquid is 0.872 kilograms per liter. I can then pop that in to my chart. I have my liters. I have my 0.872 kilograms. This tells me then that the mass entering is 1,744 kilograms per hour. Okay, so now that I have that information, I'm going to update my diagram showing the mass flow rate. That way I have all the information in my diagram so that I can quickly look and see what's going on. All right, now I'm ready to write my mass balances. Remember, accumulation equals input minus output plus generation and consumption. My accumulation is 0. My input into this distillation column, right? This is where I'm going to do my mass balance, is 1,744 kilograms per hour. I have mass 2 flowing out. I have mass 3 flowing out. Okay, so if I look at this, I don't have enough information. I have to do additional mass balances. Now, because there's no generation or consumption, there's no reaction, I can do an individual mass balance on the butane and the toluene, right? B and T. So I could have how much butane is accumulating? Well, it's 0. How much butane is entering? It's MB1, right? So I have M1, but I'm specifically referring to this as the butane by setting, writing that B down there. I have 2 flows of butane out, right? M2 and M3. So now I have an additional piece of information. I can do the same thing for toluene, where I now have my T in there so that I know that I'm thinking about toluene entering and exiting my system. I can write down a few extra equations. I know that the total mass of 1 is the mass of the butane and the toluene. I can do the same thing for mass 2 and mass 3. All right, so let's look at our degrees of freedom. I knew one piece of information. I have 8 unknowns, 6 equations. I need a little bit more information. These aren't going to sum to 0, right? I have to pull out more information. For right now, I'm going to put, I want to focus on the B balance because that I knew the most about, right? I had more information about it because I knew information about the composition here, here, and here. So for right now, I'm going to put the total mass balance and the toluene's mass balance up in the right-hand corner just so that we don't forget about them, but we're not, they're not crowding our workspace. Okay, so let's look at what's happening over at the inlet side. All right, so I'm going to try to get as much information out of here as possible. So we know that for every kilogram entering, 0.45 kilograms are B. So the mass flow rate of B1 is 0.45 kilograms of boron per total times 1,744 kilograms per hour. This leaves me with 784.8 kilograms of that uh, benzene per hour entering. Okay, great. I now know more information. I also can look down over here. I see that the MB3 has 8% of the B in the feed, right? So that means that MB3 equals 0.08 times MB1. Well, I now know what MB1 is. So I can do 0.08 times 874.8, and I can determine how much B is exiting through the bottom, which is 62.78 kilograms per hour. Okay, so now I have information about B input, B coming through the bottom. I want to now tackle what's happening at the top. Well, I can do my mass balance. There's no accumulation. What's coming in is MB1. What's leaving is MB2 and MB3. I know how to solve this because I have MB1 and MB3. So 0 equals 784 minus MB2 minus 62. Therefore, my mass leaving through the top of species B is 722 kilograms per hour. Okay, we're making progress. I'm going to just store those mass flow rates for the B species up in the right-hand corner. And let's go back and talk a little bit about our total and our toluene set, right? So these are the equations that we have left to use, and I've got all this information sorted over here. Okay, let's use the information about B in stream 2 in order to get this M2. We were told that 0.95 of M2 equals B2. Well, I know what B2 is. So I can go through, I can rearrange this equation, and I can find that my flow rate of out the top is 760 kilograms per hour. If I know how much is leaving, what the total M2 is, I can solve for M2, right? Because the total mass, M2 equals B2 plus T2. Well, I know M2 and I know B2. So I can rearrange. I can find that the flow rate at T2 is M2 minus B2, which equals 38 kilograms per hour. Again, I'm going to put that information up here in terms of the individual flow rates, and then I can label in my diagram what M2 equals, which is that 760 kilograms per hour. Wonderful. We are cruising now. We can go back to our mass balances and start plugging in the information. Right? If I look at my total mass balance, I know that 0 is what's coming in, so that's that 1700 minus what's coming out, that's that 722 minus M3. Hey, one equation, one unknown. I'm ready to solve that one. I can look at my T species. I have 0 equals mass flow rate of T1 minus mass flow in M2 minus M3. I have one equation, two unknowns, so I'm not quite ready to solve that one yet. So let's solve for M3 first. So M3, we had the 1744 kilograms per hour coming in, 760 kilograms per hour leaving. In addition to this unknown M3, rearrange my equation, and we'll find that M3 is 984 kilograms per hour. So I can now label that in my process flow diagram. All right, now let's go back to our T mass balance. That's the last thing we didn't know. I have 0 equals the mass of T coming in, the mass of T leaving through M2, the mass of T leaving through M3. Well, I still know a fair bit of information that I haven't used, namely the fact that I have 0.55 kilograms of toluene of T per the total flow rate in. And I also know that the total flow rate in M1 equals B1 plus MT1. I can use either pieces of information. They should put me in the same spot. Using this sort of total mass compositional space on this flow rate in, we have 1744 equals 784.8 plus MT1. Therefore, my mass flowing in is 959.2 kilograms per hour. I can take this, substitute it in up here, and I'll find that my mass flow rate leaving out the bottom in terms of T3 is 959.2 minus 38 is 921.2 kilograms per hour. Okay, so here's my final mass balance and detailed flow diagrams. I know my masses in each flow rate. I have the species-specific mass flow rates. I've answered all of the questions. We often want to check our work. So to do that, I can go back in. I should be able to take all of this information, plug it into these equations, and either these ones should be 0 or I should have the correct total. Okay, so this is our first, this is our exemplar mass balance on a single unit. All right, so we used the mass balance on the total mass flowing through the system. We used information on the mass of the individual species moving through the system. Okay, and then we used other information such as composition of the individual streams to solve out our problem. All right, so let's go through. I'm going to just do this really, really quickly and not go through the details, but if I were to put into words and in a process what we did, we sort of looked at what was coming in, right? So what was coming through the system, we determined how much mass was entering. We drew that flow chart and labeled everything, the masses, the percentages that we knew. We looked in terms of variables of what we were looking for. We did our degree of freedom analysis and looked to see if we had enough information or if we needed to, gather more. We determined that we needed we didn't have all the information, so we needed to go through, pull out some additional information. Then we finally solved our equations. We calculated the quantities we were looking for, and then we could make sure that the final result was in the units and form that was asked. Okay, so in a chemical plant or any system really, you generally don't have just a single unit operation. You generally have a bunch of things that are all happening simultaneously. So we can have multiple units happening. I can have, say, 2 feeds which are coming, they mix together. Then that mixture enters some sort of unit one, which may, have two outlets, say a product one and some sort of uh, secondary stream. That secondary stream can have, say, a splitter, which splits um, the stream into two. I could then have a second, product stream exiting the system. And then whatever's left would go into unit two. That unit two could have, feed that's going into it to then produce product three. Right? So how can we do this? Well, it's going to be the exact same idea that we took for a single unit, but I have to do this on multiple places. I'm going to break up this problem into individual points of mixing or of individual points of balances. And then I can derive my equations on each one and move forward. Right? So I could do a balance over the entire system. So that would say, feed one, what's going in is feed one, feed two, feed three. What's coming out is product one, product two, product three. I could do it a balance on this mixing point, right? So what's going in is feed one and feed two. What's coming out is, this stream. I would label that individually. I could then do a balance on unit one. This stream is entering. I have two streams that are leaving. I can do a balance on this split point. I have whatever's leaving unit one up here. It's broken down into, product two and whatever's entering unit two. And then I can do another balance over here, right? So I have all of these places where I can do a mass balance, and that can be a total mass balance and or individual species balances. Okay. And this doesn't have to be just a single, 2-unit system. I can extend this into larger and larger and larger systems, looking at complex chemical processes with multiple mixers, settlers, distillation, moving things around. Okay. Um, I want to I forgot to make one comment. Because we've gone through this and due to time constraints, I'm not going to show you examples of how to do this, but it's the exact same idea. You can take, you know, any of these and start thinking about how you would go about solving it. It's the same thing that we talked about for a single unit, just more complicated with the number of equations that are needed. Okay, so let's go ahead and look. Some additional just vocab that I'd like you to be aware of in types of streams. One is called a recycle stream, um, where part of a stream is put back to an earlier point. So this is pretty common in chemical reactions, right? In a single pass, we don't necessarily have of this going through there. We don't get the conversion that we want. So we might take some of that material coming out and send it back to go through that unit again. Okay, so we can also have a bypass where a fraction skips a unit. So instead of going through, a certain portion comes through and then it's mixed in downstream. All right, so that covers our very quick-paced overview of mass balances. Hopefully now you feel comfortable with unit conversions, interpolation, the equation of chemical engineering. We've went through detailed examples of doing a single unit mass balance, and then using degree of freedom analysis. And then I showed you the concept of doing multiple unit operation balances. With that, I'll remind you to take the quiz, and I will see you next time.